guys, welcome to the first lab session for COMP389-589. Today we're going to be looking at the use of SQL within the PostgreSQL database management system. So the content for today's prac actually comes from Chapter 4 from the prescribed textbook from the Fundamentals of Database Systems by Masri and Navath. So today we're going to go through a few introductory points just about using Postgres and using the PSQL interactive client, and through that you'll learn how to create your first database. You'll create some tables. You'll be mostly working on the company database example that we've looked at in the last couple of lectures. You'll be inserting some data into those tables, and then you'll be going through and doing some exercises where you'll be doing some basic retrieval queries. So first of all, welcome to the practical classes for COMP389-589. Over the course of the trimester, we'll be covering the basic use of structured query language and using PostgreSQL. We'll be looking at developing some database-driven applications in Java, and we'll also be looking at database-driven web applications using PHP. And then we'll finish up with a couple of very specialist topics. So we'll be looking at using NoSQL databases, focusing on the MongoDB NoSQL DBMS, and we'll also look at some spatial databases using the PostGIS extensions for PostgreSQL. Each of the lab sessions will have a single video accompanying them, and there'll be a series of exercises for you to complete that go along with the notes and the exercises. So all of the lab exercises should be completed using the software installed on Turing, so that's using Postgres 9.4 and the versions of PHP and Java that are on Turing, because that's where your assignments will be marked. So in today's practical, we'll be focusing on using some of the utilities with PostgreSQL. So we'll be looking at the interactive query tool, the PSQL program, and you'll also be using the createDB and pgdump utilities. And we'll be introducing you to the first, the basic SQL data definition language and data manipulation language statements. So moving on in to today's content. The first thing we're going to look at here is actually creating your first database. So before any relations or any tables can actually be created and data entered in, you have to have a database to work with. Now, the easiest way to do this is to use the createDB application that's bundled with the Postgres applications. So the createDB is just a utility that's bundled in with Postgres DBMS, and it can be launched from the command line. So if you go in and get your terminal open, you can simply type in createDB, and it expects one command line argument, or at least one command line argument, which is the name of your database. Now, your users on Turing have been set up so that they have all of the permissions within Postgres to create databases, so you don't need to put any additional information in there. So if we go over to our command line, we can just go createDB, and I'm going to call this mwelch8 prac 01 demo. So when that completes, it doesn't actually return anything to the screen. So if there was something that went wrong, it would have returned an error. It just gives you your prompt back. You can then log in using the PSQL interactive client. So to check that your database was created correctly, we can then go and log in. So mwelch8 and you can see there that we've got some information about Postgres, the PSQL tool that started here, and we've now got our PSQL prompt up here. So you can see that the prompt is different from the standard Unix one. So the PSQL tool is just another utility. It's the interactive query utility that's bundled with the Postgres database management systems, and allows a user to access the database via the command line. So the PSQL query tool expects at least one command line argument, and that particular command line argument, as you saw, is the database. Now, remember that on Turing, your accounts have all been set up with the appropriate permissions and roles within the Postgres database management system, so you don't need to put any additional connection information such as usernames and passwords in there. So any database you create, you will have access to that one by default, so you won't need to put passwords and bits and pieces in there. Another point to note is everyone is sharing the Postgres instance on Turing, so any databases you create are visible to other users, but they won't be able to log into them. So the only implication that will really have on you is that you won't be able to create databases that have the same name as some that already exist. So that's why I put my username into the database name. So if you go through and put your username into the name of every database that you create, you shouldn't have any problems. Note that the PSQL utility has a full range of command options there, so you can go through and review them on the PostgreSQL documentation here. So you can see here there's all sorts of flags and bits and pieces that you can specify on there that you can for the interactive tool. So PSQL has a full range of commands, and you can view them using the /? command. You can see here that it actually brings up a list of all of the possible commands that you can use while you're in the PSQL tool. Note that these aren't actually SQL commands, these are just commands, they're utility commands that are specified within the PSQL utility. So the most common ones that you will be using is the /DT command. This actually allows you to view all of the available tables in your database. The /DV command lists all of the available views, and /Q will exit your current connection to the database and exit the current instance of PSQL. Later on, you'll be looking at the copy command, and you can also use the /I command to actually execute the SQL statements in a .SQL file. So once we've created our database, we can now start to look at creating some tables. And we do that in SQL using the create table command. So it's used to specify a new relation, giving its name and specifying a list of attributes and their types with the syntax listed here. So you can see here we've got our create table keywords, followed by our table's name, we've got our brackets, and then we have an attribute list with each data type. Now Postgres provides a full range of data types. So with our numeric data types, we have our small integer, real, float. We also have a long data type there. We have some character data types, so character and varchar. We also have bit strings, boolean, so true, false values, date and timestamp data types. And you can view the full list of available data types from the Postgres documentation. So if we jump in here quickly to the integer data types, we can see we've got this nice table up here that indicates the precision or range of our integer types. So you can see that a small int is actually a 16-bit integer, an integer is a standard 32-bit integer, and a big int is a 64-bit long integer, and we've got reals, which are a standard 32-bit floating point number, and our double precision, which is actually a standard double, which is 64 bits there. So you've got all of the data types analogous to those found in most programming languages. Another interesting one here is the serial data type. So this is a standard integer that's actually auto-incrementing. So you can use that to create serial numbers that increment automatically every time you actually insert a record into those into your table there. So moving back to our exercise here, please note the precisions and ranges of some of those data types can be implementation specific. So as we saw in the Postgres implementation, they're 32-bit, but if you move to another database management system such as Oracle or MySQL, the precisions and ranges of those particular types might change because that's implementation specific. So be aware when you're writing SQL that things may be a little bit different across your database management systems there. So moving forward, when we're creating our tables, we can actually specify a full range of constraints on those tables. We can specify default values for particular attributes. we can specify primary key attributes, which are the same as primary keys that we discussed in the relational model earlier in the previous lectures. We can set up relationships between tables using foreign keys, and we can use check clauses to actually create checks on particular attributes to ensure that they adhere to business rules specific to our application. So the first one we're going to look at here is the default. The default constraints. So setting a default value for a column is achieved using the default constraint. And essentially, after your attribute, you simply specify the default keyword followed by your value. So we don't have an example of that one here, but essentially if you want to just chuck in, all you do is chuck in a default and then the value that you want to assign to the particular attribute within your create table statement. You can also specify that a column should not accept null values using the not null clause. So you can see here in the create statement for the department table. So this department table is taken from the company database example that we've been looking at over the last couple of lectures. We can see here we've got our set of attributes listed on the left hand side here, and then we have our set of types listed on the right hand side here. And some of them actually have the not null specified here. And we've also indicated a primary key down below, so we'll get to those in the next little section here. But by specifying this not null on the attribute, we're actually indicating that we're not willing to accept null values or blank values into that particular attribute. So if we try to insert a record into this table, and these particular attributes don't have a value specified in that particular record that we're trying to enter, it won't. The database management system simply won't allow it. So primary keys, recall from the previous lectures that primary keys are used to uniquely identify individual rows or individual tuples in our relations, and we can specify them using the primary key clause in Postgres. So effectively, the easiest way to specify them is to list your attribute name, your attribute type, and then just have the keywords primary key. The second way to do that is to set them as a named constraint. So we do that by using the constraint keyword, giving the constraint a name, specifying the primary key constraint, and in brackets the attribute name. So both of these result in the primary key being specified as my attribute for our particular table. So we can see above here there's a third syntax similar to the constraint syntax here, where we specify the primary key and then the attribute within some brackets there as well. So we'll see some examples of those particular syntaxes in the database below here. So you can see here we've used, for the project table, we've used the primary key syntax after the actual attribute type's been specified, where in the dependent table we've used the alternate syntax here, specifying the primary key after the attribute list, because we've actually set our primary key to consist of multiple attributes. So in this particular table, the dependent table, the primary key is the combination of the dependent name and the employee serial number. And we've specified that that combination must be unique for every row within that table. So once we've got, so in addition to our primary keys, we can also specify unique attributes. So the unique keyword is used to specify alternate keys. Remember that a relation can have multiple keys in the relational model, and only one of them will be the primary key. If we want to specify alternate keys, we can use the unique keyword and list that after our attributes and type within our table create statement. So only unique values will be able to be inserted into the my attributes name column with that constraint in place on a particular table. So to set up relationships between our tables, we actually use foreign keys. In particular, we use the foreign key clause. So the foreign key clause, specified using the foreign key keywords, we then specify the attribute within the actual table that references our second relation. So we put our references keyword in there, the second relation that's actually referenced, and the attribute within that relation that is actually referenced. So a table can have multiple foreign keys to different tables. So you can link tables up in a range of different configurations. And effectively the syntax looks like this below. So here we have an example of the employee table being created, and we've specified our foreign key using the foreign key keywords. we're indicating the super serial number, super SSN column, is the foreign key that actually points back onto employee itself to the actual serial number. Here we have an example of where the department number, the DNO field, actually references the D number field in the department table. So recall that when we're actually inserting, deleting, or updating a record within a table that references another table, that's referenced by another table, a referential integrity constraint can be violated. So the default action by the Postgres database is actually to restrict any such update, insertion, or deletion that actually voids an integrity constraint. So if we were to, for example, from our employee table, to delete a particular employee that's referenced by another employee via this relationship, it would actually restrict that and actually not allow it to take place. Sometimes that's not always desirable, and as a result, the SQL and Postgres actually allows the database designer to specify other actions to use in that situation, and they're referred to as referential triggered actions. Now, the operations that are available are set, default, set null, and cascade, and the actual triggers for those operations are on update and on delete. So on update and on delete, as the keywords indicate there, occur on update and delete of the particular attribute respectively. So if we make an update to the employee serial number of a particular employee, then the on update action will be actually fired off. So we can see the actions we have here are the set default, set null, and cascade actions. Now, set default basically resets the value of the referencing tuple to some particular predetermined default value that you actually have to specify in the constraint. The set null operation actually sets the referencing value to null, and the cascade operation actually updates the referencing tuple, the referencing attribute, to actually reflect any updates to the referenced tuple. So, for example, down here within our employee table, we've actually got we'll look at the second foreign key that's been defined here. So we've got the department number, which actually points to the D number field in the department table. And we can see here, on delete, we're actually setting null. So if we delete a particular department that's pointed to by an employee via the DNO field, it will actually set the value of the DNO field to null if the tuple in the department table that it points to is deleted. If we update a department number in the department table that's pointed to by the department number field here to another value, that update will actually be cascaded back to the DNO field in the employee table. So if we change our department number, if we update department number 5 to be department number 6, all instances in the employee table that have a department number that point to the actual department number 5 will be updated to number 6 for us. So it's good to have that one in place so that all of the updates will actually be carried over there. So we can see here, as I've just walked through, in the employee table, we've set on delete, set null, and on update set on update cascade, so that the changes will be reflected on an update, and on delete they'll be set to null. So any tuples of employees referencing that one will be set to null there. So we can go through and set up our tables. Our employee database, which you're going to go through here in a later exercise, looks like this. So we've got 6 tables here to create. We've specified all of our attributes. We've specified our foreign keys that link them all together. So recall from the lectures that there was a nice diagram that had all of the tables pointing to each other. This particular diagram this particular set of foreign keys reflects that diagram, and you'll be going through and creating that shortly. Before we get to that, we're going to look at inserting data into our database. So once a table structure has been created, we have to actually insert some data into the tables. And that can be achieved by either using the insert SQL commands or the copy SQL command. So the insert command can be used to create individual rows of data in a table, and it has the syntax indicated below here. We have the insert into keywords followed by the table into which we want to insert the row of data. Then we have a bracketed, comma-separated attribute list. And this list is actually optional, but it allows us to specify which attributes our comma-separated value list is going to be actually inserted into. So we've got the values keyword here, and then we have our bracketed, comma-separated list of values that we want to insert into our attribute list here. So, for example, the value in value 1 will be inserted into attribute 1, value in value 2 will be inserted into attribute 2, and so forth, all the way down to value n being inserted into attribute n. So we have an example here. To insert the record Richard Marini with department number 4 and serial number 56356333867 into the employee table, we'll specify that we want to insert into the F name, L name, department number, and serial number fields using our comma-separated attribute list. We then have our values keyword, and we have our comma-separated list of values here. So that record will be inserted into that database table. So as I mentioned before, the attribute list is actually optional for the insert command. You don't have to have it there, but if you don't have the attribute list there, you have to supply a value for every column in the table. If you miss one, the insert won't be allowed. So points to note about this one are, so string, date, and timestamp type values are single quoted. So you can see here that the FName, LName, and SSN, which from our definition up here we can see are varchar, so variable character types, and character types in the case of our serial number, they are surrounded by single quotes indicating that they are a string value. Integer and floating point types or numeric types don't have to have the single quotes around them. So you can see we've got our department number there, which is specified as an integer type, doesn't have that particular set of double quotes around it there. Other points to note, SQL is case insensitive. So you've probably seen that I've been using a mixture of upper and lower case for the keywords for the SQL commands. Postgres doesn't care about that. You can use either. I've used mostly uppercase just to indicate that they are keywords. That's a good convention to have. But table names are also case insensitive, so if you put in an uppercase for the E in employee, it'll still be recognized as the employee table. If you want to recognize case sensitivity in employee and attribute, in table name and attribute names, you actually need to put double quotes around the table and attribute names. So just remember that when you're creating your tables, everything's case insensitive and it's all treated as lowercase unless you double quote your identifiers there. So the alternate approach to actually insert data into your tables is to actually use the copy command. Now the copy command is designed to read data from a flat file. And we can do that, and flat files include comma-separated value files or XML type files like Microsoft Excel files. The copy commands are usually specific to comma-separated value files though, but you can have other delimiters as well. So a comma-separated values file looks something like this. So if we go to the department locations file here, you can see that we actually have a simple set of records listed in there that actually allow us to specify a record for our table on each row. So each row is a record of data and there's a comma-separated list for each item there. I'll go find another data table there that actually has a little bit more data in it, just so you can actually see what we mean there. So if we open up with Uni, we can actually zoom in a little bit so you can see what we mean here. So you can see if we zoom in here, we've got each row constitutes one record of data. We've got each item separated by our commas. You'll see that there are some empty data items here. If we have an empty attribute, we simply leave it as an empty spot with our two, we still have to have a comma in there to indicate that there is a field there, but it's just empty. So you can see that these particular fields are empty in these employee records. So each row within our comma separated values file will be inserted by our copy command into our table. So the copy command has the following syntax: has our copy keyword, we specify our table name, the from keyword, and we have a path to our CSV file. And then we've got these options on the end here. We've got CSV and header. Now, CSV indicates that it's a comma-separated values file. That it indicates there is actually a comma character between each field. The header keyword indicates that the first row in the file actually has the headings for each column listed. So in this particular example that we just saw in the employee table, it didn't have the headings listed. So when we go to import that particular table in our exercises below, we won't be using that particular option. But if you have the headings listed as a comma separated list in the first line of the file, you can use that particular option to recognize that within the copy command. Now, due to the configuration of the permissions with the PSQL interactive client, we actually have to use a wrapper function. We actually use the /copy PSQL command, which is a wrapper for the SQL copy command. That's because we need to that's because the PSQL client has a different configuration for the permissions to access the file system. So we have to use that particular /copy command to import data using the PSQL client. So periodically we may want to actually delete data from our table. So we do that using the delete from clause. So we have the delete from keywords, we specify a table name, and then optionally we can specify a where condition. And in here we can actually we can set a condition that actually allows us to delete a particular set of rows from our table. If we don't specify a condition, then the delete command will actually delete all rows from our table. So for example, if we want to delete individual employees, we can just use, in the condition we can put in there is where SSN equals a particular number. So if we go to our employee table, so if I log in to my table here, so let me quit out of my demo table. If I log in to my prac database, so you can see here that I've already created this one, I can actually go and view the data in my employees table. So you can see that I've got rows of data there. I'll just make my screen a little bit bigger there so that you can see what's going on with those rows of data. You can see there I've got some rows of data in my table there. So if I want to go and actually delete a column from this particular table, I can actually go delete from employee, where we might delete that column's SSN. Might delete this last tuple, we might delete this particular row of data here, so where SSN equals, now because we're working with the SSN, I'm just going to copy that one, paste him in here. Now remember that the SSN is a character field, so we have to single quote that. We can actually go through, and we can see here that we've actually violated an integrity constraint. We've tried to delete that one, so there's actually something that's pointed to that one, and we've actually violated it. So if we go back in and run our select command, that hasn't been deleted, or if it has been deleted, it's actually violated. So it hasn't been deleted because there's obviously an employee that lists that particular employee as a supervisor. So if we go through this list here, the employer SSN list here, there'll be a referential integrity constraint violation going on there. So, but anyhow, that's just a demo of the particular command, of the delete command there. So that's how we actually clear out our tables. So moving back to our lecture here. So now we've got some exercises for you. So your first task, the first few exercises are just walking you through creating your first database table and logging into that, creating your first database rather, and actually logging into that database using the PSQL client. Then you're actually going to go through and create the employee database. So I've given you all of the table create commands here. You can just go through and actually cut and paste those in. So I've got those over here already already available. So I'm just going to quit out of my current database using the /q command. I'm going to log back into my demo database so I can actually go and create some of these tables. So for example, if we want to create the first table, you can go to our exercise. I'm just going to bring it up on here because I can't cut and paste between them. You can go to my department table, grab my department table and just copy, Control-C, jump back to my command line here, paste that one in. So you can see here it puts a few funny characters in there. That's because it's skipping lines in the actual PSQL client. We can just run that one and we get this create table prompt back. When we do a /DT to display our tables, you can see that we've actually created our department table. You can go through and repeat that process until you've created your employee database. So it's important to follow through the order in which you create your table here, because you can see that they all have foreign keys. So if we go and try to create the dependent table, for example, before we've created the employee table, it won't be able to reference the employee table because it won't exist. So you'll get some errors coming up there. So go through, create those tables, run your DT command to actually view your tables. Once you've got them created, you're then going to be importing some data into those tables. So I've actually provided you with some with the data there already. So you've got the CSV files already there to download. So you can go and grab those, download them to some location in your file system, and then use an appropriate copy command. So substitute in the appropriate path name to your file to actually import those in. So you can see here, remember we're not using the header flag on our copy command because our files don't have headers on them, and remember because we're in the PSQL interactive client, we're using the /copy command. So once we've actually got that completed, we can actually go and view the data that's in there using our select command. So I'm just going to go back to my original database here, and if we want to view the data in there, we're going to have a look at select queries in a moment, but we can actually select the data using a select query. We can view our data. So if we select and we put a wildcard character to return all columns from employee, and remember we put our semicolon on the end because all of our SQL statements are terminated by a semicolon. We can run that one through and you can see we've got our data listed there. To quit out of this listing, you can just press the Q key and it goes back to give you the prompt there. We can view the contents of the project table. You can see we end up press Q to get our prompt back. So if we don't actually put our semicolon on there, you can see that the prompt will keep going, keep asking us for input until we terminate our statement. So the final couple of exercises here are for you to create your own database schema. So here we have a relational schema presented in a block diagram. So each of these blocks represents a table and each of the tiles represents an attribute within that table. So your job is actually to choose appropriate data types for each of these titles, specify your primary keys. So remember from the previous lectures that the primary keys are indicated by the underlined fields here. So you can see that the book ID in this particular table is the primary key. Specify your primary keys and then specify foreign keys. So the foreign keys are indicated by the arcs that point from a particular table from the referencing table to the reference table. So you need to set up foreign keys. You need to construct SQL DDL statements, so table create statements that create the table, specify your foreign keys, specify primary keys, specify your foreign keys, and then actually declare appropriate referential triggered actions for those foreign keys. So that one's up to you. There'll be a set of solutions available. So go through and build a set of table creates there. So remember, think sensibly about the application as to what you do with your referential triggered actions. So for example, if a publisher is deleted from the database, what should happen to the publisher name in the book field? Should the books be deleted? Should the publisher name be set to null or set to a default value? That one's up to you. And that'll be specific. That'll have to be specified for each of those fields there. So once you've constructed that, create some sample insert commands to actually put some data in there. I'll leave that up to you. That's just to show you. That's just for you to practice using your insert commands. You'll notice that sometimes there'll be a particular order in which you need to load data into your tables. So, for example, you won't be able to load a book. Any books into your tables until you have some publishers for them to reference. So if you try to put a publisher in there and you specify a publisher name that doesn't exist, you'll get an error come back. So there's an order in which you have to insert data into your library database, and the hint there is to look at the tables that are only referenced and that don't reference any other tables. So tables such as the publisher and the borrower and the loan branch table are probably safe to create first, and then you can move on and create the book copies and book loans tables and borrower tables from then on. So have a play around with that and practice some of your insert statements. So the final section of today's lab session or practical session actually looks at basic retrieval queries. So looking at our select query. Now you saw before there that I had a quick example of the select query. The syntax of the select query is basically specified here. So we have select, we specify the list of attributes from our table or table set that we want to select from, and then we have our list of tables, so we can actually select from multiple tables in the same command, and we have the condition to actually specify the actual data that we want returned, so the records from that table that we want returned. So the where clause is a boolean, consists of a boolean expression. It's actually optional, and you can use the logical comparison operators to compare attribute values with each other and with literal values. So, for example, here we've got some SQL queries. Get started here. If we want to select all columns from the employee table where the DNO, the department number, is equal to 5. Oops, we can do that. Remember, we terminate with our semicolon, and we can go through and you can see that there's actually 4 records that have a department number of 5. We could go through there and actually put some column lists in there, so we might only want the F name and the L name. Oops, L name from that particular relation. So if we go through, we can see there that we've actually restricted our query to only return those 2 columns. That's actually called projection when we restrict the number of columns we return, and it's called a restriction when we limit the number of records there. And we'll become more familiar with that as we move through the next couple of pracs, where we look at more SQL and we actually look at the relational algebra topic as well. So couple of points to note here. So you saw the wildcard operator in action before to get all columns. You can also use the distinct operator to remove duplicate records from the query. So, for example, if we select salary, from employee, you can see that there are some duplicates in there, so you can see that there's 225,000s listed there. So there's some duplicate records in the return values given back by that query. We can remove those returns those duplicates by using the distinct clause. So if we put the distinct clause in there, you can see that the duplicates have now been removed. So we're only returning 32 rows, where in the original query we were returning 40 rows of data there. So you can use the distinct clause to remove your duplicates there. You can actually order your columns, or order the results returned using the order by clause. So if we go back to our original query, we go order by salary. You can see that it's ordered from smallest to largest. So you can see you've got all the 25,000s, 29 all the way up. Again, if we remove the duplicates, you can see that we've now got our ordered list, and we've only got all of the unique salaries that are in that particular table there. So it's a fairly handy command to have in order to restrict the duplicates there. So now I've got some examples for you to try here. These are taken straight from the textbook, and there are actually additional examples as well. This is just a selection to show you how a few different, how some of them work. Go and actually reopen my prac here. If I bring this one up, so the first example here actually looks at selecting the birth date and address from employees where we've got first name John, middle initial B, last name Smith. So if we go and grab that particular query, we can just cut and paste that one into our command window here, and we can see that we've actually returned the birth date and the address for our employee there, for our John Smith. Now we can actually confirm that by just going back through here, and we might just put the wildcard operator in there just so we can also, just so all of the columns are returned. So you can see there that we've filtered on these ones so that that particular row of data is returned. In the second example here, we're actually joining two tables together. There's actually an error in this one. That shouldn't be single quoted. We're selecting the first name, last name, and address from the employee and department tables. Now, we only want to get we only want to return the first name and last name and address of employees that are in the research department or the department with dname research. And we actually link the two tables together using this clause here. So if we go and grab that particular SQL statement there, we can drop that in, just remove those single quotes. So if we run that one, you can see there we get an error. That's because it's trying to treat that as a character, not as another attribute. So you can see there that we've returned all of the first name, last name, and addresses from people that work in the research in the department with dname research. Now it's important to link the two tables together. Link the department number from our department table to the department number in our in our employee table there. Otherwise, if we don't have that particular clause, we'll actually get the union of those two returns. So if we remove that clause, return that, you see that we get every possible combination of columns returned from all tables involved there. So you can see there that by putting that in, we're actually linking. We're saying we only want tuples where the department number from the department table equals the department number in the employee table, and we're also restricting on the dname field from our department table. So it's important to remember to link all of your tables through. We've got some similar examples here. So return the first and last name along with the immediate supervisor for each employee. So we can go and grab that one and run that one as well. Drop that one in. You can see there that we've got first and last name of each employee, and we've also got the first and last name of the supervisors. Now, some interesting syntax there in that query. We've actually given the tables an alternate alias within the query here. So you can see we've got our employee and our employee tables. So we're linking a table to itself. And in order to achieve that, we've actually specified that the first employee table is actually going to be known as the E table using the as keyword, and the second one is actually going to be known as the S table. So you can see here we're linking the supervisor serial number from our employee table to the serial number of the S table. So we're basically saying the supervisor of this employee is linked to the serial number of this employee. By linking those together, we can see that we return the employee and the name of their supervisor. So you can see here that some So we've got an employee can actually supervise multiple other employees as per the relationship there. So you can see this particular individual here actually supervises these three employees. The final example here shows how to link multiple tables together. So we're actually linking 4 different tables together here. Remember that we have to link all of them together, and we've actually got the AND operator, the AND logical operator there to link all of our items together there, so that we can see that we're linking the serial numbers from our works on table to our employee serial number. We're linking the works on project number to the project P number field, and we're linking the department number in the department field to the employee department number. And when we run that particular query, we'll return a list of all employees and projects they are working in, and we've also got an order by clause in there to make sure that they are ordered by alphabetically by the first name, by last name, then first name, by department name, sorry, last name, then first name. So you can see here that they've ordered by the department name, then the last name, then the first name there. So fairly straightforward. And we've got just showing how to link all of the tables together and put it all together with an order by clause. So now we have some exercises for you. So after you've completed and run through those queries and got them working, you've got 3 SQL queries to go through and build here. You've got to retrieve all of the names all of all employees in Department 9 who work more than 10 hours per week on product, the project product. Oops, zoom out there. On the Product X project, list all the names of employees who have dependent with the same first name as themselves, and list the names of all employees that are directly supervised by Franklin Wong. Now remember that you have to run all of these queries within the same database that you've already created all of your tables on. So don't expect to create a new database and find your data in there. You have to make sure you run it on the one that you've created beforehand. Now the final little task I've got for you here is to actually run the PG dump utility. So the PG dump utility can actually be used to obtain a backup of your database. It actually produces a whole list of SQL commands to recreate your database from scratch. So you can run that by basically running PG dump, and then you put the name of your database, and then you forward the output to an SQL file. So I've already done that. And you'll end up with, if you go and actually view that in a text editor, so if you go and view it in gedit, you'll end up with an SQL file. So within that SQL file, you'll notice that you have all of, where is it here? It's db.sql, so if I open that one up, you can see here that we've got some SQL commands. So there's some up here that you've never seen before. These are just setting some items up for your database. You've then got some table create statements here, but you'll notice that there's no primary and foreign keys and no constraints specified except for the not nulls that have been put in there. So you can go down, you can see all of those. There's some alter statements to set the users. And then there's actually these strange copy statements here, and it's actually using these to copy the data in. So it's setting standard in and then actually running that straight through, piping it straight in and terminating with a null character there. And then it actually goes through afterwards and actually specifies all of your primary keys and then all of the foreign keys right at the end. So that's after all of the data's been imported. So go through and examine that file and have a look through, and you'll notice that there'll be subtle differences between the table create statements and what we actually put in there. And that's because the statements are being converted into some sort of internal representation, and then they're being extracted from that internal representation back out by the PG dump utility into an SQL file there. So go and have a look at that. So that's all we've got for today's exercise. The solutions will be available shortly on the site for that one. So thanks for coming along. Remember to read Chapter 4 and have that open beside you while you complete this exercise to make life a bit easier. So thanks for tuning in, guys.